We are live. All right, let's do this. I'm going to show you how you're going to graph your data, and then I'm going to show you kind of what it means. Okay? I'm going to show you some different scenarios for motion. The first one we're going to do is the easiest one. Okay? This is if something's not moving. That's really, really easy. Okay? So you can see here we have time. We have distance. Time should always be on the x-axis. We have distance, we have acceleration, we have speed. Okay? You'll notice that the speed is always 0. So in other words, not moving. There's no acceleration. The object is always 10 meters away, I don't know what direction. So if I was to graph this, all I have to do is highlight what I want to graph. And I'm just going to go to Insert. And I'm going to go to Chart. Remember, I'm recording this, so if you forget, it's all there. And I'm going to wait for nothing to happen. Oh, here we go. Okay. And then I'm going to ask for a scatter plot. Okay. And this is what it looks like. Now, I'll make this a little bit smaller, just so you understand what's going on. You'll notice that these are the points. I could ask for what's called a trend line, so I just got to click on the dots, and then you'll notice that all the stuff on the right opens up. I'm going to scroll down to a trend line. It's going to give me a line of best fit, and then I'm going to ask for an equation, and there it is. Now, was my object moving? No. The slope of this line is 0. There's your, if you look up here, right, if you look closely up here, you'll notice it's in the y equals mx plus b. Some of you are starting to sweat. You're like, oh no, not this again. So the slope is 0 because it's not moving. This is a distance time graph. Distance is on the y-axis and time is on the x-axis. It's not moving. That's the easy one. All this scenarios you were doing in your lab, things are moving, right? So it's obviously not going to look like this. But you should know what not moving looks like. So you know what moving looks like. So let's look at the next scenario, okay? And remember, I'm recording all this. So if you're like, too fast, it's okay. It's going to be there, right? And I may send you the link if you're nice to me. Okay, so here's a different one. What if we are moving at a constant speed? All right, and you'll notice... So constant speed, so be careful how you read that. It's not constant speed up. It's just constant speed moving up. Okay? Up. Meaning I'm going to say up is a direction. Okay? Because then I can show you what going the other way means. So you'll notice we got time, 1, 2, 3, 4, 5. We got distance, 0, 10, 2, 3, 20, 30, 40, 50. Here's my speed. You'll notice the speed is the same. And if the speed is the same, that means no acceleration. The speed doesn't change. Okay? So what this means is, if I'm traveling at 10 meters per second, then every second I move 10 meters. So you'll notice that we're always increasing by 10 meters. If something's moving at a constant speed, this is what the graph's going to look like. So again, I highlight, insert, chart, scatter plot. There's my chart. And I can click on the dots. Actually, let's first look at the graph itself. You'll notice that it looks like a diagonal line, right? Okay, so let's click on the dots. Okay, and I'm going to ask for, again, a trend line that, in this case, fits perfectly. So obviously that's got to be the right trend line. And then I'm going to ask for an equation, okay? And here is my equation. Okay, so let's take a look. So there's my equation. Y equals mx plus b. You'll notice the slope is 10. Well, because what is this? This is distance on the y-axis and time on the x-axis, right? And what was our distance changing by? It's changing by 10, right? If I move the graph, you'll notice that the distance is changing by 10. Right? Every second the distance changes by 10. So, that's constant. Now I want you to look at the next one below it. I already did this one, okay? What is similar about this? Yeah. Yeah, but you'll notice the numbers are the opposite, right? It starts at 50 and it's changing by 10, but in a decreasing manner, right? 50, 40, 30, 20, 10. The other one was increasing. If I look at this graph, you'll notice that it's the same slope, but negative. It's negative 10. Y equals mx plus b, right? Now, think about that for a second. They're both speeding up. Sorry, they're not both speeding up. They're both moving at a constant speed, right? But one is negative and the other one is positive. So, because in physics, the negative sign only means the direction. That's all it means. So, that's pretty significant actually. But, like for example, if up is positive, then the opposite of that, down, is negative. That's what the negative sign means in this case. It means down. Okay? So the first example was what? Not moving. These two are moving at a constant rate. Up versus down. Okay? Now, let's see what happens if they're not moving at a constant rate. In other words, they're accelerating. So let's look at this one. Okay? This one is speeding up, going up. Okay? Speeding up, going up. Now, your ball, when you drop it, do you think it's going to be speeding up, going up? No, it should be speeding up, going down, right? But let's take a look at what does speeding up, going up look like. Okay, well, here are some numbers. But maybe I should explain to you how I actually got these numbers. So you're like, where do these numbers come from? So I'm actually going to erase them, just so... Okay, so take a look at our speed, okay? Do you remember the concept of average speed? Average speed, if an object is speeding up, in this case, is it speeding up? What do you think? Yes. It is, right? You can see that this object, in other words, if I take, let's say I do this, I copy this, let's say I copy, I'm going to put it over here, okay? I'm going to paste it over here, and I'm going to do this, I'm going to copy that, and put this over here, and let's say now I know I want the distance time graph, but let's say I graph the speed time graph, okay? Well, just by looking at it, what is it going to look like? Just by looking at the data, what should you get? You'll notice it's going to be what? Diagonal line, right? Now, if it's a diagonal line, what did I say you can do? When the speed is changing at a constant rate, what can you do? Or can you get the average speed in this case? Yeah, what's the average speed? It's the midpoint. In this case, it's the midpoint of 0 and what? 50, right? For these 5 seconds. So if I said to you, how far does this object travel after 5 seconds? It's actually easy. It's just the midpoint between 0 and 50 is 25. So 25 times 5 is 125 meters. So if we do this correctly, we should get 125 meters by the end of it. Okay? So let me get rid of this graph because that's actually not what I'm graphing. So I'm going to delete it. Okay? So let's look over here. So let's say we start at 0 time, 0 seconds, with a 0 speed and acceleration is 10. Okay? After 1 second, my speed is 10 meters per second, right? But here's the question. What's my average speed between 0 and 1 second? Start at 0, I go to 10. It's my average speed. 5, right? And you remember that distance is just speed times time, right? So after 1 second, I traveled 5 meters. Because it's average speed times time. The average of 0 and 10, the average of these two numbers is 5. So 5 times 1 is 5. Don't worry, if you're confused, you'll catch on to the pattern, okay? Let's look at the next second. Between 1 and 2 seconds, okay? What's my average speed between these two numbers? It's 15. So how far do I travel in that 1 second? Well, distance is average speed times time. So 15 times 1 is 15, right? But I already traveled 5 meters here. So now I travel another 15 meters. So now I have traveled a total of 20. And if you're still confused, don't worry, you'll catch on to the pattern, all right? Look at the next second. In the next second, I go from 20 to 30. It's my average speed. 25. How far do I travel in that 1 second? 25 meters. But I already traveled 20, so now we're at 45. Now you're starting to catch on, I hope. In the next second, what's my average speed? 35. But I already traveled 45, so that adds up to what? 35 and 45 is 80. Do you remember what I said to you? If you take the average of 0 and 50, it's 25, times 5 seconds, we should travel how far? 125 meters, right? Okay, let's see if we get there. What's the average of 40 and 50? 45. In that 1 second, between the 4th and 5th second, 1 second, I travel 45 more meters. That gets us to 125. But the difference is this shows us the change in the speed, the change in the actual pattern of the distance changing over the time. Because now, look, if I graph this, because if I just do average speed times the 5 seconds, it doesn't really tell me what the pattern looks like. But if I do it every second, you'll see this. So watch. I'm going to do the exact same thing. Scatter plot. Okay. Now, take a look at the scatter plot. You'll notice that it doesn't quite look like a diagonal line. So if I went and I clicked on the dots, okay, and it asks for a trend line, you'll notice that, don't look good. There's something really odd about this trend line, right? This is not the right trend line. This is looking at something that's linear. It's not linear. So I'm going to show you something called a polynomial, which if you know your math, you should be familiar with this. Basically, this is the equation that best fits this curve. And if I ask for the equation, so use an equation, this is what you get. But let's actually take a look at this. Okay. Well, what is this? Okay. You see this? This right over here? Okay. Let's do something. Because I can't use my pen here. So I'm going to export that. I'm going to section. So now I can draw on it, okay? This is basically 10 to the negative 32. See that? E to the negative 32. In other words, that's so tiny, we can just simply ignore it. Do you remember in chemistry class when you added up the mass of the atom? Remember you never added up the weight or the mass of the electron? Because your teacher told you that the mass of the electron is what? So tiny that you could what? Ignore it. Right? Kind of like how I ignore you guys. This number is even smaller than that. This number is so small we can simply ignore it. Which then leaves us with just this. Y equals 5 5x squared. That's what it leaves us with. Okay? 5x squared. Now, do you remember the x squared, if you remember in math class, the x squared gives you a what? A curve, right? Okay. Now, do you recall the acceleration? What was the acceleration for this data set? It was 10. All right? You'll notice this number. When you get this curve and you ask for a polynomial and you get a trend line, the value of that is x squared. The number in front of it is actually half of the acceleration. In other words, the actual acceleration of this line is double the number you see that's in front of the x squared value. So, if you get a graph, and this is y equals 2x squared, the acceleration is actually 4. If it's 3x squared, the actual acceleration of my object is 6. Because one of the things you got to do is graph your data and then derive the acceleration. Now you know how to do it. You're going to graph it, you're going to see a curve. You're going to get a line, a best fit. You're going to get an equation. You're going to see an x squared value. Your acceleration is going to be double that x squared value. That's how you're going to get it. Okay?